In the last video, we looked at how a single beam of light can be made up of many different colors, and by breaking up that light and looking at the spectrum of the light, we can learn a lot of information about where that light came from and the environment that that light was produced in. So one of our first questions should be, well, how is light actually produced and in what sort of situations? And one example of it that I want to talk about in this video, you've probably seen before if you've ever looked at the element of a stove or the embers of a fire. And that's that as an object heats up, and for example, I have a picture of a furnace here. As an object heats up, eventually, if you get it hot enough, it will start to glow, starting at a deep red color, and then as the temperature continues to increase, it'll become a brighter yellower color. And this phenomenon is referred to as blackbody radiation. Blackbody radiation. And the interesting thing about this is that for objects that are made out of different materials, for instance, the brick of the side of this oven and the metal that has been placed inside of it, objects that are made of different materials will, as long as they're at the same temperature, have the same brightness for their glow and have the same color for their glow, even though they're made of different things. So let's talk a little bit more precisely about what we mean by a black body. So let's say I have some object. I'm going to assume that this object is an ideal absorber of radiation. So an ideal absorber. And what I mean by that is, let's say I have some red light that's being shone on this object, and I have some yellow light, and I have some blue light. If this is an ideal absorber, all of these wavelengths of light are going to be completely absorbed by this object. Nothing is going to be reflected off. And since nothing is going to be reflected off, that means that this object is going to be black. No light is reflected off of it, so all I see is just blackness when I look at that. Now, no objects are actually ideal absorbers. Even things like charcoal, which is very, very close to being a true black body. There are going to be slight differences in it, but as a kind of approximation, this works very well for a lot of objects and sometimes things like stars and distant planets. Okay, so we have our ideal absorber and light is being shone on it, and as this light hits the object, the energy from that light is going to be absorbed into the atoms that make up this object, and it's going to cause it to heat up. And as it heats up, eventually this object will start to glow, and it will start to give off light. And this light that my heated object gives off is referred to as blackbody radiation. Now, one thing that I should say right off the bat here is whenever we're talking about temperatures in physics and astronomy, we're always using what is known as the Kelvin scale. We don't use Celsius or Fahrenheit, we use degrees Kelvin. And the way that we look at degrees Kelvin, a change in 1 degree Kelvin is the same as a change in 1 degree Celsius, but the Kelvin scale starts at absolute zero. So 0 degrees Kelvin is absolute zero. You can't have a temperature lower than that. That's when all the atoms in your object have completely stopped moving. And that temperature corresponds to negative 273 degrees Celsius, approximately. It's 273.15 something, I think. So all of our temperatures are always going to be in Kelvin unless we say otherwise. So for a long time it was known that these glowing objects, these heated objects will start to glow, but it wasn't until 1900 that a guy by the name of Max Planck was able to come up with an equation which describes what the spectra of these objects, heated objects look like. So again, for this spectral graph, we have the intensity of the light, at each color. So the x-axis is wavelength, and we see that part of the light was in the visible part of the spectrum. This is the infrared. And all the light that is at shorter wavelengths, this is mostly UV light, and there's a sliver here that's X-ray and gamma rays, but the light at these temperatures, we don't get into that part of the spectrum. So what Max Planck kind of showed is that these lines can be completely described just by the temperature of the object. So the spectra just depends on temperature. And there's a couple of things that we notice about this. First, if I have a cooler object, less light is going to be given off. So if I have a hotter object, so I'm going to say as temperature increases, the object gets brighter, more energy is being given off at all wavelengths as we increase in temperature. So this bottom line is 4,500 degrees Kelvin. This middle line is 6,000 degrees Kelvin, and this top line is 7,500 degrees Kelvin. So we notice that as the temperature increases, the brightness of the object increases dramatically. And we also notice that as my temperature increases, the point where the wavelength where most of the light is being given off goes to shorter and shorter wavelengths. So we have shorter wavelengths. So this, for instance, for a human body, the temperature is not very high at all. We don't give off very much light. If you turn the lights off, then you can't really see it. But if you look at the human body with infrared goggles, you'll notice that the human body does give off light in the infrared part of the spectrum. We just can't see it because it's not in the right part of the spectrum. And if I have, say a very, very hot star, then it might give off light mostly in the UV spectrum. The sun gives off a little bit of light in the UV spectrum, but mostly in the visible part of the spectrum. So we notice that as temperature increases, the object gets brighter, and the wavelengths that most of the light is being emitted at are at shorter wavelengths. So if we see the spectra of an object, and it is close to what a black body is, we can use these graphs to match up what the temperature of that object actually is. So if we look at an example, this is a picture of the spectra of the sun. So this jagged line is actually the spectrum of the sun, and this smooth line is the spectrum of a black body at 5,777 degrees Kelvin, which is about the temperature of the surface of the sun. Now we notice that this line doesn't match up perfectly with the spectrum of the sun, which is because our sun isn't a perfect black body. It's fairly close, but nothing is. There are very few things that are perfect black bodies. But even though it's not a perfect black body, it does do a fairly good job at approximating the spectrum that we see from the sun. So when we see the spectrum from distant stars, we can do a similar thing. We can observe their spectra and try to match a black body spectrum to that to figure out what the temperature of that object is. And from that temperature, we find that if we know the temperature, we can say something about how bright the object is, and that can help us learn other things about the star. So we still haven't described how these spikes in our spectrum occur, and we'll talk a little bit about that in the next video.